Hi, Assalamu alaikum and good evening. Today we will present our project title Enhancing Electric Power System Stability through the Implementation of Energy Storage Systems (ESS) in Electric Vehicles Charging Infrastructure. Before we dive into the details of our project, I'd like to take a moment to introduce the members of our team. First, Sidi Nur Aisha Mohammed Noor, second Dr. Mohammed Abdul Talib Mat Yuso, third, Dr. Mohammed Iqbal bin Zakaria, last, Dr. Nick Hakimi bin Nick Ali. I will discuss 5 parts in this project. First, introduction, problem statement, objective, result and discussion, and last conclusion. For introduction, as part of Malaysia's commitment to reduce CO2 emissions by 40% from 2005 levels by 2020, the adoption of electric vehicles, EVs, is a key strategy. However, the increased uptake of EVs creates significant challenges for the power grid. Fast charging stations put high demands on transformers and power lines and leading to uncoordinated EV charging that causes power losses, peak demand issues, and voltage violations. These issues ultimately affect power system stability and infrastructure longevity. This study investigates the impact of EV charging station behavior on the distribution network. EV charging introduces increased losses, grid instability, and reduced power quality and efficiency. The integration of EV charging stations strains power grids, causing voltage fluctuations, equipment overloading, accelerated aging, and harmonic distortion. The objective of this study is to identify the optimal location of energy storage systems, ESS, using the evolutionary programming, EP, technique. This aims to mitigate the negative impacts of EV charging on the power grid. The methodology involves, first, developing a test system on a distribution network using Octave programming. Second, developing evolutionary programming, EP, to improve the EV charging profile to minimize power losses and maintain minimum voltage levels. Third, identifying problems in the test system based on 30%, 60%, and 100% penetration of EVs. Lastly, results are discussed in terms of active power demand, power losses, and minimum voltage under different EV penetration levels, 30%, 60%, 100%. This is figure for low voltage distribution network. A distribution network with feeders A, B, C, D, and E, serving 7, 4, 6, 3, and 2 houses, respectively. To address the challenges identified, we implemented several mitigation measures. For 30% penetration, ESS charging and discharging ensure more stable power demand, especially reducing peaks in early morning and late evening. For 60% penetration, ESS installation reduces peak demand around 8 p.m. and smooths out fluctuations, resulting in a more stable voltage profile, lower losses, and improved efficiency. For 100% penetration, before ESS installation, power demand shows more fluctuation and lower values. After ESS installation, power demand appears more stable and consistently higher, suggesting that ESS helps maintain a consistent power supply. For 30%, 60%, and 100% penetration levels, power losses before and after ESS installation are observed, indicating improved power system stability with ESS. Minimum voltage improves significantly after ESS installation. At 30% penetration, the minimum voltage improves from 2.9525 to 23.959. At 60% penetration, the minimum voltage remains unchanged at 23.96 before and after ESS installation, indicating full stabilization. At 100% penetration, the minimum voltage remains at 23.966 before and after ESS installation, confirming the system stability. The project successfully optimized EV charging infrastructure to enhance electric power system stability using ESS and evolutionary programming. Integrating ESS significantly improved power system stability by reducing demand fluctuations. Comparing power demand before and after ESS installation showed smoother demand curves, reducing peaks and troughs. Thank you for your attention.